Hello everyone and welcome back to another video. So while I was kind of on that break from uploading, I managed to solve the hacknote challenge from Pwnable.tw, which is a use after free vulnerability, and I didn't really know much heap exploitation before starting this, but I knew use after free was like a common thing. We even see a double use after free in the new Bluekeep exploit on the Microsoft RDP service, so clearly it's still relevant, so I figured it would be worth learning and doing. But before I did hacknote, I did this challenge here from Protostar, heap2, which is also a use after free CTF. So the way this challenge works is basically this stuff is pretty self-explanatory. You enter the while loop. It reads your input, sees which command you're using, auth, reset, or service. If it's auth, then it will allocate a chunk on the heap with for the structure as well, and it'll put your username on there or what you passed to auth. And then if it's reset, it will free the auth object from the heap, but it won't reset the pointer, which is where the vulnerability is. And you can see here, examines what can happen when heap pointers are stale. So this is like a hanging pointer, which means that when str_dup is called, and it places the string onto the heap, it means that it'll be put at the same location as the auth object, which means that if you write enough bytes into that freed memory, you can modify where the auth integer would be, changing its value, and then if you call login, you satisfy this conditional here and you've logged in already. So we're going to do that real quick before doing the other one. Let me just get out of GDB. So heap2. So we just have to authenticate, and then reset to free, to call free, and then service. And the reason you need to call it service multiple times is to actually write past integer, because you still have to go through into the actual modify where the actual integer would be on the heap. It's not just right at the start of the memory block. And then if we call login, maybe a little more. And then it says you have logged in already. So that's a basic use after free. I'm not going to spend time stepping through with GDB. Now we want to look at hacknote. So here's hacknote. They give you the libc and the binary, and it says a good hacker should always take good notes. And of course it's running on a Docker. So the first thing to do is to open this up in IDA and start reverse engineering it, which I've already done. So we can just take a look at what happened, or at what I did. And I got kind of like a semi-dark theme. I like it, but hopefully I can find one that makes all of this area dark as well. So looking at the functions, we're going to start in main. And the first thing main does is it calls getUser function, which is a subroutine that will find out which what you want to do. So if we run this, you see we have several options. We can add a note, delete a note, print a note, and exit. So just to demonstrate its functionality, if we add a note, then we're asked for the size, and let's just say like 16, and then also the content, and then it says success. To print a note, you just choose 3 and give it the index of the note, and then blah blah blah. And to delete a note, you give it the index and it deletes it. And 4 is just exit. So that's basic functionality. So when we enter the main function, we're going to jump into this menu. as you can see right here. So it's going to compare our input to 2, and if it is 2, then we're going to jump to delete note, which we'll call the deleting note subroutine. If it's not 2, we're going to compare it to 3, and if it's 3, we're going to jump to the print note subroutine, which we'll call that. If it's 1, we're going to add a note, and then if it's 4, we're going to exit, which you can see here calls exit. So I renamed all these subroutines, like print note, more choices, blah, 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 delete note, add note, because you always want to rename your functions when you're reverse engineering, blah, blah, blah. You guys already know that. So, and then you can see that all of the subroutines, after they're finished, will go here, which just jumps back to the top. And that makes sense because if we run hacknote and we just do that, if we just do one of the choices like add note, then it returns back to the menu. So it makes complete sense that it jumps back to get user function. So now let's take a look at the different functions. So when we add a note, the first thing we do is we compare the current number of notes with 5, and if there is less than 5 notes, then there's room to make another note. If there's more than 5, then it's pretty obvious what it does. It just prints full, and it will throw an error because you can only have 5 notes at a time. So if it's not full, then we're going to go through all this, which doesn't really matter. This is just the part where it sets up the structure, and then this is the important part here. So we're going to call malloc well, there's 2 malloc calls. There's one here, and the other one is here. So the first malloc call will be the actual structure itself, which has a pointer to the print function, which we'll go over later, and a character pointer to the content. And the reason I know it's 2 pointers is because it's performing malloc on an 8-byte block, which means that you just need 2 pointers, 4 bytes each. But we'll go over how I knew that these were the print function pointer and the character pointer to the content later. So if malloc succeeds, then it will go to this here, which will malloc the size of the note and the actual where the actual contents will go. These comments were actually already here, but I added these ones. And then, yeah, this is all pretty self-explanatory. And then if that succeeds, then we jump to this subroutine here, which will ask for the content, and it'll move the content to the allocated chunk up that was called up here. Alright, and then this exits and it goes back to the get user function. So that's the rundown of add note. It's pretty readable, like it's pretty easy to tell what happens. So reverse engineering wasn't that hard. Moving on to deleting note. So deleting note will ask you for the index, as we saw earlier, and then it'll basically just zero out the memory of where the content of the notes would be, blah blah blah, and then it'll free the note content first, and then it will free the structure, which the first malloc call is being freed here, and the second one is being freed here. So this is important because in the fast bins, since the fast bins are first and last out, that means that the actual structure will be the first fast bin, and this will be the second one. So just keep that in mind for later. Let's see what else is here. And you can see the pointer that's in EAX is never cleared out. So we have a potential use after free again, just like the other Protostar one, where we have a stale pointer. But moving on to printing a note, again it asks for the index, pointer to the note, and then the thing you had to see here, this is all self-explanatory, is that it uses call EAX. And normally you would think that for printing a note, it would use a function like puts or printf, but it's using call EAX, which means this is some sort of function pointer. And you can see EAX is loaded with a local variable offset, and what that tells us is that this basically confirms that there's a pointer to the function that prints notes in each structure, because if it's a local variable, then it must be dependent on the context that the subroutine was called in, which means that it's dependent on each different structure. So the so call EAX here refers to the function pointer, which is part of the structure that we saw earlier in adding note here. So it's an integer pointer to the print function. Let's see, where were we? Printing note. Yeah, that's pretty much all I needed to cover there. Yeah, the function pointer, blah blah blah. So obviously if we can overwrite the function pointer, then we can get code redirection. So moving on to how we actually exploit this, let's take a look at my exploit here, vim hacknote.py. So each node in the heap has 8 byte for headers, which is the struct, and then the content for the note. So what we're going to do is we're going to add 2 notes. We're going to call delete on both of them and free their memory. And then we're going to reuse the that memory location by making a new note. And when you call malloc with like a size, it'll check the fast bins in this case for a chunk of free memory with that same size that we can use. So we're gonna create a new note with size 8, meaning that fast bin layout. The fast bins it's a linked list of free chunks. So the old note struct, the content, and then the content, which means that when we make a new note, the structure section of the note will become the content of note 1. So what we're going to do is we're going to add 2 notes, we're going to free both of them, and then we're going to make a new note. And when we make a new note here, because of the fast bins, the contents of the new note get placed in the struct space of note 0, and then when we call print note 0, it's going to basically do this. Print note 0 will just call the function pointer, which we see here, with this as the parameter, which is basically the note's content, a pointer to the note's content. You can tell that because again here, this blah blah blah. So that means that we can replace the address of note 0's function pointer by allocating a new note and basically using the freed memory again. So it's another use after free, just a little more complicated. So in the main function of the exploit, we add 2 notes with size 16, the contents don't really matter. Then we free both of them. Then we add another note with size 8. And the contents we add are, this is the address of the print note function, and this is the address of libc puts. So the function, you only have 4 bytes available to pass an argument to the function, because of the way that, because of the struct only has 8 bytes available on the heap, if you remember. And then what we do is we call printnote with index 0, which uses which refers to the used memory. So we're using the freed memory, which now has this as the function pointer, and this is the argument, which means we're going to print the contents of the global offset table entry. So we're going to leak a libc address, we're going to receive it, unpack it, blah, 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 and then we're going to calculate the libc base. Since they gave us the libc, it's very easy to find the offsets from puts to libc base, from system to libc base, blah, blah, blah. I'm not going to go over that. Basically, you just use object dump, and then print that, blah, blah, blah. Delete that note, and then add a new one, but this time instead of writing the address of the print note function, we're going to write the address of the newly calculated libc system. And this is pretty much the only way you're going to pass the binsh argument, because you only have 4 bytes available. Like, it's pretty much forced to do it some way like this. And then we're going to call print note, which, now that we've overwritten the function pointer with this here, remember, because of this here, because of this, note 0's function pointer is now system with this parameter, and then we can spawn an interactive shell. And then as far as the rest of the exploit goes, basically you just need to script it so that it interacts with the menu here, pass the size and the content for adding a note, and the index for printing and deleting one. It's pretty easy to code. So yeah, we can demonstrate this. Let's see. Python. So it prints what it's doing, adding or deleting a note, blah, blah, blah. And then interactive mode. And you can see we are hacknote. And if we go to we can see that the flag is here, and it's indeed readable. So that's that. The other thing I wanted to do is to look at the pseudocode for some of these functions, just to go over how I reverse engineered it a little more. So blah, blah, blah. Let's adding note. So here you can really see how adding note works. This stuff doesn't really matter. Here it reads the size, and then it's going first it calls malloc for the actual structure, as you can see here, and then the size, which because of the fast bins actually makes the exploit work, the vulnerability work. Yeah, the pseudocode's handy. If you look at the main function, you could do stuff like rename this. I didn't look at the pseudocode for this, but you would just rename this to user input, stuff like that, and just keep reverse engineering it. So yeah, we didn't even need to look at the pseudocode for this challenge, really, because it was pretty readable in terms of the assembly. And then what else did I want to look at? Adding note. Oh, printing note. Yeah, this is the function pointer. This is the call EAX that we saw here. So yeah, that's pretty much it. That was a fun challenge. I learned a lot about heap exploitation and use after free. I didn't really know any before that. And next I'm going to do double sort, which I assume has something to do with the double sort algorithm. And I also assume it's ROP because they gave us the libc. But yeah, hopefully I'll be able to solve that, and then I'll be back later with a video on that. So until then, I'll see you guys next time.